You ever have one of those weeks? The one where you've spent days, maybe even nights, debugging a piece of firmware? You're convinced you've got a race condition or maybe a nasty pointer bug, only to find out the problem wasn't in your code at all? It is one of the most maddening experiences in embedded development. So today, we're going ghost hunting. We're looking for the bugs that aren't really there, the phantom glitches, where the hardware itself is out to get your firmware. And look, here's a perfect example right from the wild. A user on Reddit is pulling their hair out over their 3D printer. It works sometimes, but then it fails on specific complex prints or just randomly dies halfway through. The machine reports a software error, but that random intermittent behavior, that is a massive red flag. Is it a weird software bug, or is something physical, something in the analog world causing that microcontroller to just give up? This is exactly the kind of rabbit hole we're diving into today. So here's the plan. First, we're going to define exactly what these phantom glitches are. Then, we'll go through the top 3 culprits: shaky power, failing clock signals, and, you guessed it, simple mistakes printed right onto the circuit board. After that, I'll give you a hardware detective's toolkit and some solid habits to help you build bulletproof systems from the start. Okay, let's get into it. Section 1, the ghost in the machine. This is where we talk about how a hardware problem can put on a very, very convincing software bug costume. So what is a phantom glitch? Well, the symptoms look exactly like firmware problems. A peripheral suddenly stops talking, data gets garbled, or the whole system just reboots for no reason. So naturally, you fire up your software debugger. But here's the catch. The root cause isn't logical, it's physical. It's buried down in the analog domain, that messy world of voltages, timing, and noise that your debugger is completely blind to. All right, let's meet our first major suspect: unstable power. You have to think of your microcontroller's power supply as its lifeblood. If that lifeblood isn't perfectly clean and stable, your code can become dangerously unpredictable. You've seen them on every single circuit board, right? These tiny little capacitors huddled around the main chips. They're called decoupling capacitors, and they look pretty insignificant. But what happens if you pick the wrong one, or even just place it a few millimeters too far away? The answer is pure chaos. So why do these little guys matter so much? Okay, picture a modern microcontroller. Inside, you have millions of transistors switching billions of times a second. Every single one of those switches demands a tiny, instantaneous jolt of current. Now, your main power supply, it's way too slow and far away to deliver that current instantly. That's where the decoupling capacitor comes in. It acts like a tiny local battery right next to the chip, providing that instant burst of energy and keeping the supply voltage from sagging. Now, here's where it gets really interesting, because not all capacitors are created equal. Far from it. Their behavior is all about the dielectric material inside. For something super sensitive, like a clock oscillator, you need an incredibly stable C0G capacitor. For your everyday decoupling, X7R is your go-to workhorse. But if you try to save a few cents and use a cheap Y5V capacitor, its capacitance can plummet by over 80% with just a little heat or voltage. It basically vanishes from the circuit, leaving your chip completely defenseless. So when that decoupling is weak, the main supply voltage, VCC, can dip for just a nanosecond. If it drops below the microcontroller's minimum operating voltage, you enter this danger zone. It's called a brownout. The chip isn't off, but it's not fully on either. And in this weird twilight state, its internal logic gets fleeky. The delicate timing of the instruction pipeline gets messed up, and the CPU, well, it starts making mistakes. What kind of mistakes, you ask? This is how bad it can get. That tiny voltage droop can cause the CPU to misread a single bit in an instruction. Suddenly, a simple move instruction gets misinterpreted as a pop instruction. This could make your program counter jump to a totally random address it just pulled off the stack. And if that address happens to land inside your firmware's flash update routine, you've just accidentally told your device to erase itself. Congratulations, your product is now a paperweight. And it all started with a tiny, invisible power glitch. So if power is the lifeblood, the clock signal is the system's heartbeat. Let's talk about what happens when that heartbeat fails and why your microcontroller's clock circuit is actually way more fragile than you think. This right here is the Pierce oscillator. You'll find it in pretty much every microcontroller system. It looks so simple, right? Just a crystal and 2 little capacitors. But don't let that fool you. This is a finely tuned resonance circuit. Its stability depends not just on those components you see, but also on hidden parasitic capacitances. These tiny, unintentional caps formed by the MCU pins and the copper traces on the board itself. Getting this balance wrong is probably the #1 reason a brand new board appears totally dead. And getting these parameters right is absolutely critical. The load capacitance CL has to perfectly match what the crystal's datasheet says after you account for those stray capacitances. If your CL is too high, the clock frequency will be off, and that'll wreck things like UART communication. If the crystal's internal resistance, its ESR, is too high, the oscillator might just give up and fail to start, especially when it's cold. The firmware symptom? A board that just never ever boots. This brings us to our third big category of phantom glitches: mistakes printed in copper. We're talking about physical design errors on the printed circuit board that can create total chaos for the poor firmware developer. Oh man, every experienced engineer has a war story about one of these. The all-time classic is swapping the transmit and receive lines on a serial port. Your firmware sets up the port perfectly, but nothing. No data ever shows up. Even worse is a mirrored footprint, where the whole chip is laid out backwards. Or how about long SPI traces that act like little antennas, picking up noise from a nearby motor and causing random data corruption that looks exactly like a software driver bug? This bit of wisdom from an engineer on Reddit is pure gold. On your first revision of any board, just assume you screwed something up. Bringing out every single critical signal to an accessible test pad gives you a physical point to put a probe and see what's actually going on. It is the most important first step to figuring out if the problem is in your code or in the copper. So, how do we actually hunt these ghosts? Let's put together our Hardware Detectives toolkit and map out a strategy for separating hardware problems from software bugs. Okay, your two most important tools are the logic analyzer and the oscilloscope. Now, a logic analyzer is great, but it lies to you. It shows you this perfect, idealized digital world of clean ones and zeros. The oscilloscope, on the other hand, tells you the messy analog truth. It shows you the ringing on the clock line, the slow rising edges, the noise, the voltage droops, all the real-world physics that are the true source of these weird intermittent bugs. When your logic analyzer says everything is fine but your firmware is freaking out, the oscilloscope is where you'll find your ghost. Here's a systematic workflow you can follow every time you suspect a hardware problem. First, do everything you can to find the exact conditions that make it fail. Is it heat? Is it when a motor turns on? Then get out the scope. You're going to probe every single power rail looking for noise. Next, check that crystal oscillator. Is it stable? Is it at the right frequency? After that, look at your communication lines. And finally, go back to the source. Review the schematic and the PCB layout with a fresh pair of eyes. I swear, you will be amazed at what you missed the first time around. All right, on to our final section, building bulletproof systems. Because really, the best way to fix these bugs is to prevent them from ever showing up in the first place. Let's talk about the habits that will help you do just that. These are the habits that will literally save you days of painful debugging. First, be obsessed with details. Print out your component footprints at 1:1 scale and place the actual part on the paper to see if it fits. Number 2, always add test pads on your first revision boards. 3, for anything sensitive, follow the manufacturer's layout guidelines to the letter. A great firmware tip is to read the MCU's reset flags when it boots up. It might just tell you that the last reset was caused by a brownout. And finally, the most important rule, read the schematic, then have a friend read it, then sleep on it and read it again. At the end of the day, as embedded engineers, we live right on that razor's edge between hardware and software. Your most brilliant, elegant code is only as good as the copper traces and tiny components it's running on. So the next time you're staring down a bug that seems to defy all logic, just stop for a second and ask yourself, have you checked the foundation?
If you like this one, the YouTube algorithm says you're gonna love my other videos, so go check them out.